First of our presentation today is on fire-resistant enclosure of ductwork by Gavin Williams of 3M. Gavin's presentation will discuss what type of ducts and buildings may need fire-resistant enclosing construction. Gavin will talk about current technologies, the advantages and disadvantages, and fire testing requirements and compliance with the New Zealand Building Code Clause C, AS2. Gavin's presentation has been audited and has 5 CPD points as a 30-minute presentation. Gavin's joining us today from Sydney. He has worked for 3M for the last 18 years and the last 4 specifically with passive fire protection. Gavin holds a BSc in Chemistry from Wollongong University and a Master of Business and Technology from the University of New South Wales, and is currently completing a Masters of Fire Safety Engineering, the University of Western Sydney. So Gavin, welcome. We'll just bring you up on screen now. There we go.
Thanks,
Hey Gavin, great to have you here. Hope you and the family are all safe and well in New South Wales.
Yes, yeah, we're doing well.
Yeah, great.
Thanks.
Well, looking forward to your presentation. Over to you.
Great. Oh, thanks, Matt. Thanks for the opportunity. Just to start off with, I'll give you a bit of an overview of where I fit into and where 3M fits into fire protection. So 3M, our passion for science and innovation spans the enterprise, but we are organised around 4 global business groups to best serve our customers. So each of our business groups help customers find solutions, big and small, to help improve various aspects of your life, from safety equipment for workers to post-it notes that you may have on your desk. And so 3M Science is never far away. We have 4 primary business groups. It's the safety and industrial, we have a transportation and an electronics business, a healthcare business, and a consumer business. And our fire protection products fall within the safety and industrial business. So we're here today to talk about fire protection of ductwork, and I thought I'd take a step back and talk a little bit about building codes and how building codes tend to have originated. And did you know that the earliest known building code comes from the Code of Hammurabi around about 3000 BC, and some really interesting clauses in that code. Number 229, if a builder has built a house for a man and his work is not strong, and if the house he has built falls in and kills a householder, that builder shall be slain. So some pretty explicit words there describing the outcomes of dodgy building. Another one there, 233, if a builder has built a house for a man and his work is not done properly and a wall shifts, then the builder shall make good that wall with his own silver. So that's a great example of how far building codes date. In relation to fire, we have some interesting historical events. The fires of Rome in 64 AD, with the devastation of Rome then, Nero implemented some codes relating to fire and separation of buildings and different issues relating to the types of materials for some of these buildings, even as far back as then. And also the Great Fire of London, some realisation of additional safety requirements through those devastating events. And so now we have arguably more advanced building codes in relation to fire. And I'll talk about that. So what we have building codes in relation to fire especially is that society adopts the principle that the loss of life due to fire is unacceptable. And the mechanism to be able to achieve that and satisfy those principles is that governments create frameworks to achieve this. And this is in the form of building codes that are enacted by legislation. Modern building codes in Australia, New Zealand and throughout the world typically contain clear statements of the objectives that are to be met for safety and methods or techniques for how these are to be met. Now, this can be a variety of methods. On the one hand, you can have performance-based fire engineering that might be specific to a particular building, and the outcome of that is that fire engineering or performance-based methodology or alternate solution is designed to meet those objectives for fire safety. On the other hand, there can be prescriptive standards or explicit code-based requirements that are deemed to comply. That is, they can apply to a wide range of situations and buildings, and they too can be used to meet the requirements for fire safety. And in some cases, it can be combinations of both. In relation to the New Zealand Building Code, the area of interest when it comes to fire safety, and in particular passive fire protection, is in CAS2, section C3, and it's about fire affecting areas beyond the source of the fire. And in C3.1, it is described that buildings must be designed and constructed so that there is a low probability of injury or illness to persons not in close proximity to the fire source. And one of the ways that we can this requirement can be met in buildings is through breaking the building up into smaller compartments, fire isolated or separated compartments. Now, there are two primary methods of fire protection. One is active fire protection, which can involve automatic sprinklers through detection methods, and it could also be firefighting actions from the brigade, or also someone in the building that has access to a fire extinguisher. They're active methods that require some kind of action for that method of protection to work. Passive fire protection, however, is a method that of constructing a building such that the various elements, the walls, the floors, doors, for example, are designed in such a way that the fire is slow. So it doesn't fireproof, nothing's completely fireproof, but these elements give a duration through which fire will not pass. So in that way, we can create compartments or fire cells that give a duration of protection or separation. Again, back to the New Zealand Building Code, the separation of different occupancies is usually required. So if you have a residential occupancy above a eatery or some retail, then those occupancies have to be separated, for example. But in some cases, large single occupancies also need to be separated depending on the type. So if it's the floor area is too large, then it might need to be split into smaller compartments to maintain the fire safety. So when we're talking about the separation of different occupancies or splitting up the building into fire cells, that's done with what we call fire separating elements. So that can be a fire rated wall or a fire rated floor or a ceiling that resists the incipient spread of fire. So we term these the duration of fire protection that these provide in terms of the fire resistance rating. And the fire resistance rating is a duration, and I'll talk about that in a moment. But what you'll see is a number that in fact is a duration, and the duration is determined in most cases through testing against a standard fire test, a standard fire endurance test. So the nomenclature of the fire resistance rating, the three numbers there represent the structural adequacy, the integrity, and the insulation. So in the example there, structural adequacy, the element being tested cannot collapse in that time in the fire endurance test. The integrity talks about not allowing any sparks or gases or flames to pass from one side of the fire affected compartment to the next. And the insulation, it describes how long the element can resist the flow of heat from one side to the next. And that's usually a temperature change of 180 degrees in a standard fire endurance test. The FRR may not be an exact example of a real fire, and buildings have different fuel loads and different fire scenarios, but it's a standard method of being able to evaluate different materials and different configurations for the resistance, the duration they will separate. from another compartment. Here's some pictures showing the apparatus for the standard fire endurance test. In this case, it's AS 1530.4, a picture of that, and you can see there that there is a furnace through to which a test specimen, which could be a wall or a floor, or it could be a door, a fire-rated door, and it could be a wall element that's penetrated with items such as pipes and ductwork. That element is bolted onto that furnace and subjected to that fire endurance test. And you see here, I've got a graph showing the temperatures that element is exposed to. And after 2 hours, we're up to over 1,000 degrees of temperature and radiant heat. So quite onerous. AS 1530.4 describes quite a range of different elements from walls, floors, columns, beams, and in this presentation we're interested in ducts, and that's in section 9 of AS 1530.4, which describes the arrangements that are tested and the metrics. So ducts are actually fairly, in principle, similar to any other penetration, surface penetration. Once a wall or a floor that has an FRR is penetrated, that fire resistance rating is no longer valid. It is compromised. And so a method of restoring that fire resistance rating is required. And for pipes and cables, we've seen presentations on fire stopping previously through the TechEd webinars. And again, in this case, it can be involve different fire stopping materials to reinstate that fire resistance rating of the wall or the floor through a combination of different materials that have all been tested in that configuration. So just to an aside, the area of the building code, New Zealand Building Code, where the test method is specified comes out of CAS2 in Appendix C. And it's interesting to note there's two methods that are described there that are suitable in New Zealand, and that's AS 1530 Part 4, and there's also NZBC 476 Parts 21 and 22. So who can provide a fire resistance rating? Well, the requirement is that only those two standards are used, and a test report from an accredited lab is required for that. However, other data can be used from other tests, but that needs to be assessed through an accredited laboratory to be able to create an opinion or a fire assessment report. And a competent authority is someone that has the relevant knowledge and experience of fire testing. So I mentioned that ductwork, in principle, is similar to other penetrations. Once it passes through a wall or a floor, that floor and that fire resistance rating of that element is compromised. So we need a method to restore the fire resistance rating. Typically, for most types of ducts, or quite a range of ducts, the method of restoring the fire resistance is through fire dampers that are installed inside the duct at the junction where the duct penetrates the separating element. But an alternative method is through enclosing the duct with a fire-resistant enclosing construction, and also dealing with the gaps around that as well. Fire dampers, no, sorry, that's the wrong kind of damper. I don't know how that got in there. Mechanical dampers, mechanical fire dampers, they work by closing the internal sections of the duct through a mechanical means. So in the instance a fire breaks out, heat, for example, may melt or damage a link that then allows, through gravity or spring, a shutter or louver to close, effectively shutting the duct to the flow of gases and fire. So if fire breaks into the duct within a affected compartment, then it can't move through to the next compartment. So the fire resistance rating of that wall or floor is is restored through that fire damper. And that's commonly a method used for heating, ventilation and air conditioning ductwork. Now, another method of fire damper is an intumescent damper, where there are materials inside the damper that, when exposed to heat, they expand. They can be 10 times or more, and they activate really quickly, and they will close the duct off by that method. And one of the advantages of that is that there's no real moving parts. So that's the two methods of fire protecting ductwork through fire dampers. However, there are quite a range of types of ducts that you cannot use dampers. They just don't work, or would impair the functionality of the duct. And an example of that is for kitchen exhaust ducts. So there's some issues there. If you had fire dampers, they might inadvertently be activated due to the hot gases from cooking and not necessarily a fire, and that could cause problems for the kitchen. And additionally, the sorts of materials that accumulate in kitchen exhaust could potentially impair the operation of a fire damper. The mechanism could be blocked and therefore may not work in the instance of fire. So in this case, commercial kitchen exhaust dampers are not to be used in those particular ducts. So that raises the question: well, how then do we restore the fire resistance rating when that duct passes through other compartments to get outside of the building? Other ducts that usually don't use fire dampers: smoke spill and exhaust ducts. Again, they need to operate or stay open in a fire, and also the structure of that duct needs to be maintained during a fire in order to adequately vent smoke from the building during a fire. Again, also supply air ducts, they also may need to stay open to supply fresh air to escape routes, stairwells and the like. And also chemical fume ducts, for example, in laboratories and hospitals, for example, there may be chemicals in the exhaust gases that could damage fire dampers if they were installed. And again, they may also need to stay open in fire mode in some cases. So we have instances where we can't use fire dampers, and Australian the AS 1668 describes where fire dampers shouldn't be used, and also describes what the alternative is. So if we can't use fire dampers to restore the fire resistance rating, the alternative is to effectively continue the compartment all the way through the building. So we can do that by enclosing the duct with a fire-resistant enclosing construction. Here's an example here of kitchen exhaust. So we've got fire compartment where the kitchen is, fire compartment 1 adjacent to a fire compartment 2, but in order to get the exhaust gases from cooking out of the building, it needs to pass through that fire compartment 2. And the solution then is to create a barrier, a compartment around the duct to effectively continue fire compartment 1 all the way out of the building. So fire compartment 2 is not affected by anything, any actions from that ductwork. So now I'll just talk about the different types, the different methods that can be used to enclose fire-resistant or fire rate ductwork. The 4 most common methods in Australia and New Zealand are a plasterboard shaft, or a cementitious gypsum or vermiculite spray, mineral boards such as calcium silicate, and flexible insulated wraps such as 3M's 615 Plus duct wrap. So I did touch on AS 1530.4 and alluded to the configurations for ducts. And for ductwork, there's some configurations that need to be tested. One of them is testing for internal exposure where fire breaks into the duct. We're making sure in the test that fire doesn't break out again, we're measuring the structural adequacy, the integrity, so that there's no cracks or fire breaks out of the duct into the non-affected compartment, and also we're interested in the insulation, so that if there's any combustibles nearby, they're not ignited. And also we have external exposure, where the duct is exposed to fire from the outside, and we're testing to make sure that fire doesn't break in. Again, we're measuring structural adequacy, integrity, and insulation. And so in total, there are 4 configurations that are usually needed. So there's internal and external for both walls and floors, or horizontal and vertical orientations. So I'll just quickly touch on some of the different types of fire-resistant enclosing construction. And a shaft enclosure with a plasterboard enclosure is an effective way of separating the duct from the rest of the building, and effectively involves building a plasterboard fire-rated partition around the duct. But it requires quite a large amount of space to achieve this, and it can be complex in the construction and the build. Also, with the space requirements are usually quite limited. And in general, prefabrication is not very easy to do, so it all has to be done in situ. It can be heavy, so you might need to incorporate more support for the duct, but there's a long history of test data for a lot of configurations for plasterboard fire-rated partitions, and generally not a large significant capital outlay for building these sorts of structures. Secondly, we have spray-on systems. Generally, they're a much lower profile at 50 millimetres thick for a 2-hour fire resistance rating. Relatively simple fabrication, just involves installing some mesh and spraying, or potentially troweling a liquid material on there, sometimes multiple coats. There is some potential for off-site prefabrication, but great care needs to be taken with transportation, because it's a rigid material and there's potential for cracking or chipping. It is quite heavy. It can be. The material itself is typically 280 kilograms per metre cube. So some consideration of the supports for the duct would need to be considered, whether they need to be upgraded. With any kind of spray material, it can be messy, so you need to protect the area and cordon off large areas to avoid spray and overspray. There is some capital involved, the equipment such as mixers and spray equipment, and generally need specialist trades to spray correctly and get the right thickness. But again, with sprays, there's a pretty long history of and good test data to support a wide range of configurations. Here's a couple of pictures showing some finished or partly finished spraying of ductwork. Another method is using fire-rated boards, calcium silicate boards, for example. Again, they tend to be low profile, can involve complex fabrication because of all the joints and intersections. There is potential for lightweight off-site prefabrication, but again, it's a rigid system, so you need to be careful about not cracking and putting too much stress on it in transport. Fairly lightweight. There's a moderate amount of test data available for a range of configurations. Low capital outlay, but generally requires high-skilled trades to get it done properly, and can look quite good installed. So there's a couple of pictures there. In some cases, it might be a combination of the calcium silicate board on the outside with some high-temperature insulation on the inside. And finally, insulated wraps, flexible insulated wraps. And our product, the 3M615 Plus, is an alkaline earth silicate fibre that's encapsulated in a metallised foil scrim. Has a low profile, and so 2 layers for 2 hours. Lightweight at 96 kilograms per metre cubed, and there's about 50% of the weight of sprays, for example. So minimal to no change to the support structure. Consistent thickness for easy inspection and certification. It's readily adapted to off-site and prefabrication methods because it's a flexible system and there's no issues with cracking or chipping. Easy to handle and you can use lower cost non-specialist labour. Typically, an insulation lagger could do this sort of work, as well as specialist fire installers. There's no splatter and very little dust, very little to clean up, with no capital outlay for equipment. Here's a picture here showing some complex arrangements arrangement of ducts, all are fire protected or enclosed with 3M 615 plus duct wrap. The tools, very simple tools, typical of insulation lagging. Things like a cuphead pin welder and knives for cutting, tapes for sealing up cut edges, for example. So fairly routine material. So there's not much in the way of capital outlay involved to be able to start wrapping the duct. We also have systems where ducts can be jacketed with our VentureClad self-adhered insulation jacketing in the case where a duct may need enclosing construction and have portions of it on the exterior of the building. So testing configurations, just to show you some pictures of how we test fire-resistant enclosing construction. First picture here, this is showing the testing of a horizontal duct for internal exposure. And this, see that the lab technician has his hand on the duct, and yet you can see at the end of that duct it's red hot inside. So that's the duct wrap providing insulation to protect from heat from getting outside of the duct. And after removal from the furnace, you can see the glowing, how hot it is. Everything is glowing red hot. Just a picture here of a vertical orientation. So a duct penetrating a floor slab. And a couple of pictures showing the type of arrangement for external exposure where the duct is built inside a furnace. And so the output for those tests is some test reports that give the evidence of the fire resistance rating and the configuration and the method of installing to achieve that and repeat that on site. So a test report should contain sufficient detail that installation can match the tested prototypes or the assessed and allowed variations from the test lab. So they've just got two pictures, one showing the horizontal duct going through a wall, and the other one there just showing the arrangement for a vertical duct penetrating a floor slab. Just to finish up, a couple of pictures of some application examples. Here we've got a smoke exhaust that's passing through a corridor, and so we need to enclose this duct because it has to stay open, it can't have dampers. And in the event that people are egressing through that corridor, there couldn't be, fire couldn't break out of that duct. So it's all contained through the methods of dealing with the penetration on the concrete and blockwork wall, and insulated with 3M duct wrap, 615 plus duct wrap. This is an interesting one where a fire hydrant pump room was located below ground, so there's no not possible to get air for driving the pump through the wall, and it had to be through ducting that entered a central shaft. So the pump room is the separated compartment, and the air to supply the pump so it could operate, and also the exhaust gases had to be ducted through a car park and through which is a separate compartment. And so that was achieved by protecting the ductwork by wrapping the duct as they move through the car park. And another example where we can use duct wrap for prefabrication, where you might have a central shaft in a high-rise building where a range of services are being shared. And in that case, you can fire separate the ductwork from those other elements using 615 plus duct wrap, and that can be prefabricated to speed up the build. So I hope that you learned a few things about how ducts are treated in relation to fire protection. If you want more information on the 615 plus duct wrap, an easy way of finding that is by going to the EBOS website. You can just Google EBOS 3M and 615 plus, and it will take you to our page that gives an overview of the product with all the data sheets. Our local contact is Kelly Anderson in New Zealand, and I'm based in Australia, and I'm the application engineer looking after the product. So thank you for listening. I hope there was some insight there for fire protection of ductwork, and I hope you enjoy the rest of the day and the next presentation.
Great. Hey, thanks, Gavin. Just a couple of quick questions. Do I need to pin and band the 615 plus wrap?
Yes. So the pinning and banding, that keeps the wrap on in a fire. So we have tapes as assembly aids, but the tapes on their own aren't suitable for holding the wrap in place. So we use for vertical ducts, it's pinning on the two long sides of the duct as well as banding at 300mm spacing. But for vertical ducts, horizontal ducts, generally it's just pinning on the underside plus the banding, and that keeps the wrap in place during fire.
And one final question, is the 615 plus duct wrap material hazardous?
We always suggest you read the safety data sheet, and when you're cutting the wrap to size, there can be some dust as the inner core is exposed, and so you need to refer to the SDS. A mask, respirator is needed. Obviously, glasses, eye protection, and gloves. However, the fibre is an alkaline earth silicate which is biosoluble. So unlike refractory fibres such as asbestos, it doesn't persist in the body in the event that something is breathed in or ingested.
Okay, great. Well, thank you.
Thanks, everyone.